The conjugate root theorem says if p of x is a polynomial with rational coefficients, then irrational roots of p of x equals 0 that have the form a plus the square root of b occur in conjugate pairs. That is, if a plus the square root of b is an irrational root with a and b rational, then a minus the square root of b is also a root. And if p of x is a polynomial with real coefficients, then the complex roots of p of x equals 0 occur in conjugate pairs. That is, if a plus bi is a complex root with a and b real, then a minus bi is also a root. Okay, so let's look at an example. A quartic polynomial with rational coefficients has roots 2 plus the square root of 3 and 4 minus 3i. What are the two other roots? Well, we know a quartic polynomial is degree 4. We were given two of the roots, 2 plus the square root of 3 and 4 minus 3i. The other two roots are going to be the conjugates of those roots. So 2 plus the square root of 3 is an example of an irrational root because we see that square root. Its conjugate is the same expression with the plus changed to a minus. So the other roots of this polynomial are going to be 2 minus the square root of 3. And the other root, 4 minus 3i, is a complex root. Its conjugate is the same expression with the minus changed to a plus. So we would have 4 plus 3i. And that's a total of 4 roots for this polynomial. And since it's degree 4, when you add up the real and the complex roots, there should be 4 by the fundamental theorem of algebra. Okay, in example number 3, write the equation of a third degree polynomial with roots -5 and 2i in standard form. Now, the root -5 is not an irrational root or a complex root. So that's not, the conjugate root theorem doesn't apply to -5. It's just a single root. So if we're listing the roots of this polynomial, -5 doesn't have a conjugate pair. 2i is a complex root, and 2i is the same as 0 plus 2i. It doesn't have a real part, it only has an imaginary part, but it still has a conjugate. Its conjugate is the same expression with the plus changed to a minus. So we've got the root positive 2i, and then the conjugate of 0 plus 2i is going to be 0 minus 2i, which is just -2i. And that would be all of the roots of this polynomial. Now the instructions say to write this polynomial in standard form. But let's start with factored form. If we know the roots of a polynomial, we can find the zeros. If -5 is a root, then x plus 5 would be a factor. If 2i is a root, x minus 2i is a factor, and -2i is a root, x plus 2i is a factor. And to change this to standard form, we need to distribute. I'm going to start by distributing the x minus 2i times x plus 2i. So I'm going to FOIL, and I get x squared plus 2ix, and then minus 2ix, and minus 4i squared. I'm going to leave that x plus 5 in the front. The plus 2ix and minus 2ix cancel, and recall that I squared is equal to -1. So I end up with x squared plus 4, and that needs to be multiplied by x plus 5, and now I distribute again. So So x times x squared would be x to the third power. 5 times x squared would be 5x squared. And x times 4 would be 4x. And 5 times 4 would be 20. And that would be standard form for that polynomial.